Well, we've dealt a little bit with Kirchhoff's rules and some with Ohm's law, and we still have this question, how do we handle these complex circuits? We understand if we have this combination of resistors, we're going to have some times where the voltages have to add up to a certain value, other times where currents along different paths have to add up to a certain value, but we kind of have to have a starting point there. And generally the starting point is going to be, what's the current coming out of the battery? So if we looked at a circuit like we have up at the top right here, we might first want to know what's this current I right here. Now once we know what I is, we can figure out, well, since we have the resistance of this 100 ohm resistor, we would know the current, we'd be able to find the voltage drop there. And we could figure out, well, we know total voltage drop as we go through here and then through this resistor, or through here and then this resistor would have to be 5 volts because we go up by 5 volts. We could figure out the voltage drop across either of these, and then we'd know the voltage drop and the resistance for each of those, so we could find the current through each one, and we know that the two currents have to add up to this current here. So we can do a lot once we know that starting current, but we got to get to that point first. And we're going to use that by looking at something called equivalent resistance. So the big idea here is that whatever value we have, or whatever setup we have for this circuit, we're going to have some current that's coming out of our battery. Now we could make a simpler circuit that has just a single resistor in it, still the 5.0 volts, and we have some resistance that we'll call R equivalent, the equivalent resistance there. And the thing that makes it equivalent is that the current coming out of the battery is going to be the same as it was when we had this more complicated setup. So our goal now is to figure out, how do we determine what this equivalent resistance is going to be for different types of circuits? Now in a circuit like this, we have resistors arranged in such a way that if we followed one charge around the circuit, it would go through one resistor, and then it would go through the other resistor, and then back to the battery here. We could have a whole bunch of them lined up in a row like this, and it would go through one, and then through the next one, and then through the next one after that. Now this reminds me of like watching my favorite TV show, which is Walking Dead right now. Walking Dead's on Sunday nights, and I watch an episode every Sunday, and then I wait for a week and I watch the next episode, and then I watch the next episode. So this type of circuit is like watching a TV series, and in fact they call this a series circuit. So we trace the path of this electric charge. It goes through one, and then it goes through the next resistor. We say those resistors are in series with each other. So here, resistor R1 is in series with resistor R2. So as we have the current flow through R1 and R2, we know that current can split up if there are multiple paths, but there aren't multiple paths here. There's only one path. So all of our current goes through R1, and then all of our current goes through R2, and then all of our current goes back to the battery. Only one path, so the total current is the same as the current through each component. Alright, now we also know here that our voltage is going to drop as it goes through each resistor. So I'll just think of this as delta V1, how much the voltage drops here, and this one will be delta V2. And then I know if I followed a charge all the way around here, we have a drop of delta V1 and then a drop of delta V2, and then we go back to this battery and it takes us up by V0. I know that I have to end with the same electric potential as I started with, so I can write an expression then that delta V1 plus delta V2 has to equal V0. Or you might write this as V0 minus delta V1 minus delta V2 equals 0. It's the same equation. Our total drops and our total increases have to balance each other out. Now for each one of these resistors, we have some voltage drop, and we can figure out the voltage drop using Ohm's law. So if I rearrange Ohm's law to get the voltage drop, the equation we get is delta V equals I times R. So if we want delta V1, it's the current through resistor 1, that was just I, times the resistance of resistor 1, which is R1. And then for delta V2, it'll look very similar, just I times R2. So then I can go back to this equation I wrote a minute ago and substitute IR1 for my value of delta V1 and IR2 for that delta V2, and that's equal to V naught. My goal here again is to figure out an expression for I ultimately. So let's factor out an I, and we get R1 plus R2, and then it equals V naught. And so here our current I is equal to V naught over R1 plus R2. So now we have an expression for the current. And our goal with equivalent resistance was to find a single resistor that would produce the same current leaving the battery. Well, I've drawn that equivalent circuit here, and I've used RS as the symbol for the equivalent resistance in this series circuit, so the series equivalent resistance. Now if I wanted to find the current in this circuit, I would just do Ohm's law. I equals delta V, which will be V naught, over RS, the one resistor that we have in there. Now I can compare these two equations and see pretty quickly what RS is going to represent here. So I have V naught up top, V naught up top. In the bottom here I had R1 plus R2. In the bottom here I have RS. Now you could actually do the algebra here and set the two currents equal to each other, but I think we can see pretty easily that our equivalent resistance, RS, has to be equal to R1 plus R2. If we had more than two resistors, we'd write it as R1 plus R2 plus R3 plus however many resistors we have. So in general, we write RS equals the total of all the resistors. So sigma with I down beneath there for all the resistors Ri. So if we have 10 resistors, I could be 1, 2, 3, 4, 5, 6, 7, 8, 9, and all the way up to 10 there. That's our series equivalent resistance. So let's put this into practice then. I have this circuit with 3 resistors. They are in series, I can tell, because our current goes through one resistor, and then through the next resistor, and then through the next resistor. There's no splitting of the current here. That's a series circuit. So we start by figuring out the equivalent resistance for this series circuits. That's RS, and that's going to be equal to R1 plus R2 plus R3. So that's 100 ohms plus 75 ohms plus 25 ohms. And so our equivalent resistance is just going to be 200 ohms. So then we can draw a new circuit. Still has the 10 volts for our battery, but now we have just a single resistor, our equivalent resistance, which was 200 ohms. Our goal here is to solve for current, and current is equal to the voltage drop across this resistor divided by the resistance of that resistor. And so here our voltage drop is going to be 10 volts. Our resistance is 200 ohms, and so our current is going to be 0.050 amps. Now let's consider this circuit. Still a 2-resistor circuit, but we can see those resistors are organized a little differently. So if we follow our current, we don't go through R1 and then through R2, or R2 and then through R1. It's now an either-or situation. So if we watched one little charge going around here, it has a fork in the road, and it can either go down this path or it can go down this path. So instead of this being like watching episodes in a series of a TV show, this would be like different channels on TV. So you can watch one channel or you can watch the other. Okay, now the analogy breaks down because we have DVR and we have picture-in-picture, but you get the idea. It's a binary, it's a choice. There's one or the other here. And so when we have a split of our current, we think of that, or we call that then a parallel part of our circuit. And usually we draw it that way too. This path and this path are drawn parallel to each other. This resistor and this resistor are parallel to each other. Now, how we draw it doesn't determine whether it's parallel or series, of course, but it is useful to draw it that way to remind ourselves, yeah, parallel geometry terms, we know those ones. So it's just about whether we have a single path or multiple paths. So this then is a parallel circuit. We have the same goal now. We'll work to the same goal in this circuit. We're looking for the equivalent resistance, just a resistor, the value for a single resistor that would replace these two and produce the same current coming from our battery. Now the thing that makes a parallel circuit different from a series circuit, as we said, is that the current splits up. So I don't want to have just I going through each resistor. I'll have I1 and I2. And so if we trace these back, I2 starts right there. And I1 starts right here. We have this junction right there, where I splits into I1 and I2. So I can write an equation that the total current, I, has to be equal to I1 plus I2. That's Kirchhoff's junction rule. Alright, now how big are I1 and I2? Well, we can figure those out with Ohm's law. So I equals delta V over R, but what's the delta V? How much does our voltage drop as we go around this circuit? Well, if we trace a charge around any loop, we start at this point right here. We go down by some voltage that we could call delta V1, and then around here back to our battery and up by V0. And we have to end at the same voltage that we started at. So delta V1 has to be the same as V0. If we went around a different path through R2, we drop by delta V2, and then we go up by V0. So delta V2 has to be equal to V0 as well. So let's label those as well. We have a V0 drop here, and a V0 drop there. So now I can write Ohm's law for resistor 1. We'll have delta V1, which is just V0, over R1, and delta V2, and then I2, which will be V0 over R2. And so we can go back to the equation we have in green and substitute V0 over R1 and V0 over R2. Now remember, the goal is to get a single resistor that produces the same current as this combination of resistors. So we'll call that the parallel equivalent resistance now, RP, for the variable. And so in this equivalent circuit, we could write that the current, I, is equal to V0 over RP. We need the current to be the same either way, so we can set those two equations equal to each other. V0 over R1 plus V0 over R2 equals V0 over RP. Or if we divide everything by V0, we get 1 over R1 plus 1 over R2. If we had 3 resistors in series, we'd have plus 1 over R3, and so on for any other resistors we had, equals 1 over RP. So in general, we'll write this as 1 over RP equals sigma I 1 over Ri. So 1 over R1 plus 1 over R2 plus 1 over R3, and so on like that. So now in this circuit, if we want to find the current leaving the battery, we'll start by finding the equivalent resistance. So that's Rp in this case, because we have resistors in parallel. I can tell because our current splits up to go between these three. Can't go through all three at once. It has to go through, I can't go through all three in series. It has to go through one or the other or the third one. So we'll use the equation 1 over Rp is equal to 1 over R1, which is 50 ohms, plus 1 over 100 ohms, plus 1 over 200 ohms. Now these are set up as fractions, but it's probably faster just to solve these as decimals. So just go ahead and put this into your calculator. So 1 over Rp equals, and then your calculator do 1 over 50 plus 1 over 100 plus 1 over 200, and that gets us 0.035. And then I want Rp all by itself, so I'll multiply Rp on both sides, then divide by both sides by 0.035. So 1 divided by 0.035 is going to be my equivalent resistance, which is 28.6 ohms. So that means that I could draw a new circuit with still a 10 volt battery here and a 28.6 ohm resistor, and we'd have a current then of the voltage divided by the resistance, and so this is going to be 10 volts divided by 28.6 ohms. So our current then is going to be 0.35 amps. That's our total current. We can use Ohm's law to figure out the current through each branch of this circuit.